Welcome everyone to BigML's Data Transformations release. I'm BigML's CIO, and my primary responsibility is the development and health of our computing infrastructure, including the software as a service site BigML.com, and as well as our private deployments for customers who have strict data governance concerns like banks and healthcare industries. However, I also do a lot of training and demos and even created and presented BigML's first 11 webinars. Now, the last few webinars have been done by my colleagues Charlie and Chi Sing, and so presenting this webinar feels a bit like a homecoming, a back to basics, if you will. And that is somewhat fitting because I think the topic of today's webinar, data transformations, is a bit of a homecoming to the reality of predictive applications. Consider, in all of the hype around machine learning and artificial intelligence given to projects like self-driving cars, it is easy to forget how much preparation and failure goes into making those headlines, even when those projects are still not actually working. It's the proverbial iceberg with the small step successes bandied around in social media and the grunt work of data collection, transformation, feature engineering, and evaluations buried below the surface. But today we're going to go below the surface of a machine learning application to look closely at this ugly underbelly of that iceberg and introduce some tools to make that grunt work easier. You see, while you may know BigML only as a machine learning platform, we've actually been working directly with customers across several industries, creating fully automated end-to-end applications for many years now. And so we know firsthand the complexities involved. From the difficulty of clearly stating the machine learning task, down through data wrangling, transformations, the feature engineering, doing the modeling evaluations, finally making your predictions, and being able to measure the success of your application. And even realizing that sometimes after all that work, you end up starting over. And through our experience, we know where the effort lies. It takes about 10% of the effort spent simply getting a clear definition of what is actually being solved. And this is an important step as well because a clear definition of the goal leads all of the data collection and preparation tasks. For example, if you tell me you want to predict ice cream sales based on the time of year and the weather, then I know that I need to collect weather data. At the bottom, there is another 10% of the effort split evenly between the modeling, evaluating, and the predictions. And the remaining 80% of the effort lies within the data wrangling and transformation stages. Now, it's important to understand that this is the distribution of effort when you are using a machine learning platform like BigML. If you're still trying to roll your own modeling platform with a Frankenstein of open source technologies, then you should adjust these percentages accordingly. With that in mind, and with knowing how costly the data preparation stage is, you can begin to understand why today's release is focused on making this step as easy as possible as well. BigML's goal is to make data preparation as easy as we have already made the later portion of this pipeline, as this is the only way to truly democratize machine learning. Now, it is very difficult to do data transformations or machine learning in general without some actual data to play with. So let's look at a real-world example from our own machine learning platform. As I am in charge of our infrastructure, I am keen on ensuring that our model building is operating as smoothly as possible. And this is no small challenge. For example, our software as a service site running at BigML.com builds in upwards of 40,000 trees per day. That's trees only. No, we're not talking about any other resources, not logistic regression, deep neural networks, nothing else. And that also doesn't count our second software as a service site, BigML.com.au for the Southern Hemisphere. And for all of those trees, we need to ensure that each one starts processing and finishes as quickly as possible. Now, started is easy, using a custom blend of queue monitoring, auto scaling, and some heuristics to adjust ahead of demand. Now, I'm using the term easy generously here, as there's definitely some effort we've put into perfecting that system, but the approach is otherwise pretty straightforward. Making sure that these trees finish quickly or on time is a different problem, however. There could be platform issues or cloud provider problems or network latencies or hosts that are out of resources, etc. And now, while we monitor each of those effects separately, none of them actually answers the question, is this tree processing in a timely manner? They're all proxies for that question. If a host is out of resources, that tree might not be completed in a timely manner, but it's not directly answering the question. But what if we could predict how long a model should take based on its complexity and our experience with similar configurations? Then we could set an alarm per tree task if the time to process exceeded, say, 120% of the predicted time, or whatever other trigger we prefer. Now we would have a direct real-time measurement of progress. We might even go so far as to show this prediction to the user so that they know how long they may need to wait at the moment they submit a new task. Of course, this sounds like a machine learning problem. Okay, so we have a clear statement of the problem. We want to predict the build time for a tree based on the metadata of the task. So what is this data going to look like? What fields, when we're building a tree, might impact how long it will take to process? And the first thing is we can just look at the metadata from the data set, right? The most basic thing you might imagine. A data set that is bigger in size will probably take longer to process, or if it has more rows or number of columns. And so those will all be features that we would expect to have in our data for predicting how long these models will take to build. We could look a little deeper and say, well, the complexity of the modeling process isn't dependent only on the size. It actually depends on what kinds of features you have. So we can start building out features that have the number of numeric or categorical or date time or text fields, because that text field, for example, is going to turn into a feature vector of 1,000 token counts, or 2,000 even. And so it's going to be much more complicated in terms of modeling than it would be to have one text field than it is to have one categorical field. Now, in addition to that, there's also the metadata from the model itself, the parameters that the user selects in building the model. There's different ways that you can configure the decision trees. And so, for example, there's at the most basic, what is the objective type? Is it a classification or a regression? Are we predicting a categorical or numeric value? This may impact how long it takes to process the task. There's also all the various tree options, the node depth, how deep we allow the tree to build, whether or not the user wants to include missing splits. Are the splits being made with randomization? Is the tree being built only on a sample of the data versus the whole data set, which of course would definitely impact the computation time. But these are all features that will change our prediction of how long it will take. And from our infrastructure side, there's actually this thing called the subcluster, where we have a heuristic that tries to predict which jobs might take longer, and we send those to a bigger server. So we also need to have the feature in here that tells us which server cluster that tree ran on, because that will also impact how long it takes. If obviously it runs on a bigger server, it may run faster. And then in terms of the objective, we're going to be looking at the time elapsed to build the tree, which is easy because we actually include that. Once the tree is complete, we record how long it took. And so we already have that data nicely formatted in our database. So I've actually gone ahead and already done a data pull just with a sample from, actually it was a small sample over a couple of days. So I didn't take every tree built over every day, but I wanted to get a little bit more variety in the trees. So I did about a week or so. We're going to log into the platform now and take a look at that data real quick. Okay, so here's the landing page of BigML.com, and I'm going to go ahead and sign in. And then at the sources tab, we're going to bring this data into the platform. And I'm going to just do a direct upload. And here we have this file called tree times 1, which is the first sample, and we'll play with tree times 2 later, which is a second sample. All right, so we'll go ahead and take a quick look at this source. And you'll be able to see that it has the features that I described. So we have like the number of categorical fields. So in this first instance, this tree was built on a data set that had 4 categorical features and 16 numeric features for a total of 20 features. It was sent to the small backend cluster. It was not using sample replacement. It had a node threshold of 1,147, et cetera, et cetera. And then we have how long it took to build, which if I remember correctly, that is in milliseconds. So it was quite quick. Okay, and we'll go ahead and create a data set from this. And from the data set view, we can actually now start seeing some of the distributions for this data, right? We can see we have lots and lots of data sets that have don't have very many categorical fields. And actually there's a big spike down here with some data sets that have lots of categorical fields, et cetera. Okay, so we can get a nice sense of the distribution of the kinds of trees that we're building here. All right. The thing I want to mention while we're looking at this tree, this data set view, is that some things have changed here a little bit. Primarily, in addition to the summary statistics here, we also have the scatter plot, which is now directly embedded in here. So you can do a nice 2-dimensional scatter plot, and you can start looking at how your data is distributed in, well, 3 variables. You have an x-axis, a y-axis, and the color. We had the scatter plot before, but it was out in the lab section. So if you hadn't seen it before, it is embedded in the dataset view now as well. So that's a nice change. Also, the cloud action icon and the gear icon, these were here before, but of course, this is all of your one-click action, and these are all your configures. If I wanted to configure a model, I would go in here. But all of the creation objects that relate to creating a data set from a data set have now been moved into this new tab over here. And so we can see things like the training and test split, the sampling, the filtering, and these are our new features that we're going to be playing with today. The removing duplicates, merging, joining, aggregating, and then of course add fields, which is using Flatline, which we've had before, but is now in this new menu. So a little bit of changes in the UI just to be aware of there. So problem number one. So I could take that data set we just had and I could go ahead and build a model right now, and we could just predict the status elapsed time, which is the last field in that data set, how long each tree took to build. But the problem we have is that there might be identical feature rows in this data set. What do I mean? Well, here's an imaginary sample of this data, right? So we have a column, this number of numeric fields, the number of text, the number of date times, and the size and the rows. And those little 3 dots, just imagine there's all the rest of those features. All right, it's too difficult to fit into the slide, so I just compressed it. We'll imagine they're there. And then the last column, we have the time in milliseconds that it took to build each one of these trees. And if you look at this, you'll see that 2 of these rows are exactly the same parameters going in, but they have a different time in milliseconds that it took to build the tree. Now, there's lots of reasons why those times would be different, right? It could just be some network latency, a little bit of time getting the resource from storage and into memory. There could be many, many factors going on there. But the problem is that we have 2 rows where the features are identical and the output that we're predicting is slightly different. And how would this happen? Well, it could be imagine a user that's testing their script, rebuilding the same parameters. So they're working on a script that's building a model and they're just tweaking it, running it over and over. And so they end up building the same tree tens or hundreds of times. That's possible. There could be a machine learning class building the same model for an assignment. This actually is a very likely scenario because in our educational program, we actually have several universities that use BigML.com for teaching machine learning because the UI is very easy to interpret and understand, and it's a great way to learn machine learning. Might have users following an online tutorial or a blog post. So you could have a series of people that over a longer period of time, days or weeks, are all building the same model with the same data set and the same parameters. Or it could even be a BigML employee demoing the same data set and modeling process. In preparing for this, I've probably built this model that I'm going to build for you several times. And so in our data set, we have the exact same model being built over and over. But however it happens, this is not properly formatted for machine learning. To be properly formatted, we need to have each row is a single example that the model is going to learn from. And in this case, we could have tens or hundreds or even thousands of rows that are all exactly the same with different outcome in the prediction. How we're going to fix it? What we're going to do is a 2-step process of transforming and aggregating. I'm going to explain both steps, and then we're going to break them down and do them a little slower. So this is just an overview first to give you a sense of how we're going to get there. So again, imagine that this is our data. And the first thing we're going to do is we're just going to ignore the actual data now and just focus on the features. All right. So the first thing I want to do is take all of these features, and I want to be able to do some kind of an aggregation where I identify all the rows that are the same so that I can do something with those rows to make them into one row. And so I'm going to take these features and I'm going to collapse them down into some kind of a key. In this case, you can see the first row of features has been changed to a string, C3, F6, C8, etc. And I can do this for every row. And as long as I use an algorithm like a hashing function, for example, then I can do this in a very unique way so that every unique row generates a unique key, and rows that are the same generate the same key. All right, and we'll bring the time down as well. We'll just glue that in. And so from this new data set, we can perform an aggregation where we now collapse the rows. So we look at those 2 rows that both start with the A243. They have the same key, and so they have the exact same feature values, all right? And I can now perform some kind of an aggregation, where in this case, I turn it into a new data set where I just have 1 row for that key and the average of 1431 and 1673. So I apply some kind of a function to collapse those rows into a single row that has a new value, and now we'll be building a model that predicts the average time in milliseconds that we expect the tree to require to build. The key thing here is that all the feature rows are now unique. Now, if you happen to be an SQL expert and you're scratching your head wondering why I'm doing this way, fear not. I'm going to show you an example using the API towards the end where we'll do this in a much simpler way, all in one step. So the first thing we need to do is we need to handle that transformation. We need to be able to collapse those features down into some kind of a feature key. And so I'm going to show you how we can do that. So from this menu here, I'm going to go ahead and do an add fields, and this is going to bring up our Flatline editor where I can specify this new feature key and how we should create it. So we can give this new feature a name. We can say, okay, we'll call it feature key. That was an excellent name. And there's lots of built-in functions that we could apply, right? So there's a discretization by percentiles, for example. If we had a numeric value and we want to turn this into a classification problem, we can do some discretization. You can do replace missing values. If you have a field that has missing values and you want to replace them with the mean or the median, the minimum, et cetera, we can do that. We can do some normalization if we want to scale some numeric values down into a normal range. We could do some math functions like exponentiation or logarithms or squares or square roots. This bit here is new, the sliding windows. Now we had sliding windows before in Flatline, but they weren't available in the UI. And one of the blog posts we did in the series of 6 leading up to this release, there's a nice example of using these sliding windows in a financial analysis scenario. So if you're interested in the sliding windows, that's a great blog post to go check and read about how you can use Flatline to basically process columns of data as well as rows. All right, there's also some typecasting that you can do. You can inject random values. You can do statistics. If we want to do a chi-square, we could do that here. But we can also write Flatline formulas directly. And so this allows us to create custom functions that create new features. And in this case, that's what we're going to do. So I'm going to do this Lisp Flatline formula. And obviously I could just start typing what the formula I wanted here. I could say, hey, I want this field, foo, and I want to add it, to the field bar or something. So I would say, okay, we'll do plus, and I could start typing a formula, but we're actually going to go ahead and use the editor. So if you click on this little pencil here, this is going to open up the Flatline editor. And this is another change for this release. We've really worked on making this Flatline editor much more intuitive and being able to see the results of your formulas more clearly. And so you can see down at the bottom here, I have a sample of my data set. And so these are all of the feature columns that are in this data set. And as I create the new feature here, I'll be able to see what the output for each one of these rows is going to look like in that window below. So the first thing we need to do is we need to call out all of the features in Flatline. And there is actually a nice formula for doing that. We want them all except for this last one. We don't want to include the status lapse. That's the thing we want to keep because this is what we're going to be predicting. So Flatline has this nice function called all but, and we can just put the name of the field, which you can see will show up in the auto completion here. So I can say status elapsed. Okay, and if I just validate this expression, only if I have one quote, I can validate. And if I do a preview, now we're going to see in the sample, here's the original data set, and in this light green color are all the new features. If I now execute this Flatline transformation, these are the new features I would get. I'd get feature key 1, 2, 3, which are just a copy of all the features except for status elapsed. All right, so that formula is creating new features that are all of the old features except for that one. Okay, so one other thing we could do, some of these are numeric, some of these are some kind of Boolean values, so we could cast them all into strings. Okay, so if I add the function str, I'll cast all of those values into strings, and now you can see I have a list of string values from those features. And now I want to compress that list of strings down into a key, which we'll use a hashing function. There are actually several built in. There's a SHA-1 and a SHA-256, and there's even an MD5. But for this, we'll go ahead and just use a SHA-1. We don't have to be cryptographically secure or anything. We can validate that, and we can look at the resulting expression. And so again, this takes for every row, it takes every value, feature value, except for status elapsed, forces them all to be strings, and then computes the SHA-1 hash of that result and returns here. You can see the feature key. And we can see already this looks pretty good, right? Every value is looking fairly unique. We can see right away that there's some duplicates here. The first two rows are actually the exact same feature key, C4, EB, 5B. And if we look at the actual values, we can see that is correct. They both have the same sample rate, the same rows, the same size, the same objective field type, the same node threshold. These are exactly the same feature parameters, 1,159 categorical fields, for example. Okay, so this looks like it's working perfectly. So go ahead and accept this transformation, and then we'll create the data set. And now we're going to get, as an output, a new data set, which has the feature we've just constructed appended as the last column. And that's a good thing to remember, is that the data sets are immutable in BigML, which helps to ensure traceability, right? So I know that when I create this data set, if I come back a month from now, the data set is the same. I can change its name and a few other things like that, but the structure of the data set doesn't change. So when you make a change like this, it actually creates a new data set. That's the same for all resources in BigML. Okay, so here we have our data set, and we've got this nice feature key. And we can see, for example, that 351184B key, there's 3,762 instances. So we had at least 3,762 instances of the same tree essentially being built in this sample that I have constructed. So we definitely have this issue of multiple rows being identical. Okay, but now we need to do the aggregation step, right? We want to take that feature key and use it to aggregate things. And so to explain the concept of aggregation, we're going to use this playlist data. So we're looking at the features here. We have the content, so that like the name of the song, the genre, the duration, how long, or the date that it was played, and then the user column is what we're going to be aggregating on. So we're going to take this playlist information and turn it into characteristics of each of the users. So for example, if we want to know the number of playbacks per user, I want to know the number of times that user 1 has played any song at all. Then I could do an aggregation where we count on user. So if we do this, we can see, okay, user 1 has played 3 songs, and so the count on user is going to be 3. And if that sample I'm showing you there was the whole data set, the right-hand side would be the complete output data set of this aggregation, a simple aggregation, where I just get each user and the playlist count for each user. We could do a different type of aggregation. We could count the number of distinct genre played per user, for example. So if we do that, we get an output that looks like this. And sure enough, if we just focus on user 1 again, user 1 has played 3 songs, and each time the genre was different. So the distinct genres is 3 for user 1. Okay, you can also look for user 5. There's 2, they're both distinct, so you get 2 distinct genres there. So these are just different ways that we could perform an aggregation on data. We could count, for example, the number of missing devices per user. We see in the last column is the device they used to play the song, and we can count missing values, and we can see that there's only one missing value, and it's for user 2. And so we end up with, in the aggregation, zeros for everybody, and user 2 has the one missing value there. We could ask, what is the total duration? How long is each user listening to music? And we could probably do this over a window as well, but for this, we could just sum the duration, all right? So if we look at user 5, for example, we take 281 and 240, we add them together, we get 521. Okay, so now we've collapsed those rows. All of the entries in this playlist for user 5, we've collapsed all the user 5 rows, and the way we've collapsed them is by adding the durations together. Instead of adding, we could, of course, compute the average duration, which is what we're going to do in our example. We're going to compute the average build time for each of these trees. And so we have user 5 and 281. We average those together, we get 260. So that's another way we could function we could apply when we're collapsing the rows to combine the durations. We could look at the maximum duration, yet another way, right? So we could say, okay, user 5, what's the longest duration? In this case, it would be 281. Or we could equally do the minimum. We could say, okay, user 5, the smallest duration for any song you've listened to was 240. Okay, and we could do similar functions. We could do like a standard deviation or some kind of a variance calculation. And it's possible to combine multiple aggregations at the same time. And so let me show you an example of that, specifically with that playlist data first, and then we'll go ahead and do it on our tree data set. So I'm going to just take this data right off of the table in the slide there, and we can actually create ourselves a new source using an inline source, and we can just paste it directly in here. All right, and then we need to go ahead and create our data set. And now we're ready to aggregate. So we'll go ahead and from this menu, the new menu here, we'll select aggregate instances. We have to tell what field to collapse rows on. And so in this case, we're going to collapse on the user, as in all of the examples. And then we can define what kind of aggregations we want to perform. So for all the field types, you could, of course, do a count. So let's go ahead and do a count first. All right. And let's also do, for numeric values, we can do the sum and the average or the maximum. So let's find the total play time for each user. So we'll do total duration. Okay, so that's now going to compute the sum of the duration where the rows are aggregated by user. And if we had categorical or text fields, you could actually concatenate the values. So if you had text fields, you would end up with an aggregation where you just take the text fields and glue them together. And you can also do a concatenation with distinct values. So it would actually look at each individual value that's being concatenated and remove any duplicates. So you just have one unique entry in the concatenated output. All right, and so let's, for this one, I don't know, we could do the count distinct on the genre, for example. All right, and if we go ahead and hit aggregate instances, We're going to get a new data set as output, and it's going to have the user, and for each user, it's going to have those 3 new features. So for each user, we now have the total playlist count entries, the sum of the duration, and the distinct count of the genres, right? So we can see, for example, there are 2 users that have listened to 2 genres and 1 user listened to 3, for example. And we can export this as a CSV now, and those aggregations are all complete. Okay, so let's go ahead and aggregate our data set. Let's take our tree times extended here, which now has our feature key. And remember, we created the feature key specifically so that we could do this aggregation. So that's what we're going to aggregate on. So we'll aggregate on the feature key. And for this, remember what we want is the average. We could choose something else. So like if we wanted to be pessimistic, we could take the maximum. Or if we wanted to be optimistic, we could take the minimum. But for this, we'll go ahead and take the average. That feels like a solid bet to me, right? We want to know if we're doing better or worse than the average in general, so that's probably okay. And we're going to go ahead and apply this to the status elapsed. So now we're going to get a new data set in the output where we've collapsed the rows based on the feature key. And for each feature key, we're going to, for all the rows that we collapse, we're going to compute the average of the elapsed time. All right, so we can see that there's lots of trees down here, 2,864 instances that all happened very quickly. All right, so we get this nice output. And again, there's only 2 columns in this output now. So problem number 2. Now we have a new problem though. What we have right now is this. We have dataset 1, which is our original dataset with all of the features and the time in milliseconds it took to build each tree. And we have this new dataset which has this feature key and the average build time where we've collapsed all the rows. And so these aren't even the same dimensions anymore, and they certainly don't have the same values, because what we really want is this. We want all of the original features, right, numeric and text and number of date time columns and all that stuff, with the average milliseconds it took to build the tree that represents that metadata. That's the output we want. So we have the 2 data sets above, but we want the one below. And the way we're going to do this is something called joins. So let me walk you through how joins work a little bit. So first of all, data sets to join, they have to have a field that's in common. And that's critical. It's the field that it's going to use to combine the rows. So joining fundamentally is taking 2 data sets and putting the rows together to create new columns. And in order to put them together, you have to have a field that it matches the rows to. So it has to be able to figure out which rows match which rows. So as an example, you could imagine I want to join some sales and demographics. So I've got a table that has a bunch of information about customers that have purchased things, and I've got another table that is information about the actual customer, the demographics, and they're both keyed by the customer ID. And so in the join, I would use the customer ID to bring those tables together. Another example might be joining an employee and the budget details based on their department, right? So this employee is in that department, and from some other data set, I know that this department has this budget, and both of those tables have a department ID as the key, and so I can join them together and end up with a data set where I have the employee information and the departmental budget information in one data set. Okay, now the data sets that we're joining, they don't need to have the same dimensions. Okay, they have a different number of columns, a different number of rows, no problem. Joins can be performed in several ways. We've got a left, a right, an inner, and an outer, and there's actually even more than that if you go down the SQL rabbit hole. So let me give you a quick overview of what some of these join terminologies are referring to. Okay, so when we're talking about joins, we like to talk about data set A and B, and we're always talking about joining, taking A and joining B. All right, and when we say a left, what we're talking about is a left join of data set A to B, and it's going to look sort of like the picture there. We're going to return all records from the left A. So we're not going to lose anything from A. Everything that started in A is going to end up in the output. And what's going to happen is we're going to append all the information as columns from B that have matches in A based on the key that we're joining by. Okay, and if there's nothing in B that matches, we're going to fill in a null as well. All right, so that we can keep all the records from A. So if we start with a table A that looks like this, where we've got some ID that is 1, 2, 3, 4, 5, and a field 1, which is a numeric, which has values like 34 and 56, etc. And we left join it to B, where we now have the same IDs, but you notice it doesn't have all of them. It just has 1, 2, 4, 6, so it has no 3 or 5. All right, and it has a categorical value of red, green, blue, and black. When we do this join, you'll notice that B has, as I mentioned, has no 3 or 5. And so in the left join output, we get the original A table. Notice it still has 1, 2, 3, 5, or 1, 2, 3, 4, 5, has all the values from A. And then we sort of just glue the B column on there, if you will. So 1 is red, so it gets a red. 2 is green, so it gets a green. But 3, there's no entry in B, so we just end up with a null for the color. And the same for 5, we end up with a null for the color as well. Okay, so that is what happens in a left join. You basically get a copy of the left data set plus columns from or features from the right data set that match or nulls otherwise. Now you can imagine a right join is basically just the other way around. So this is a bit, I wouldn't say repetitive because it can be a little bit confusing when you're talking about this, but now we're talking about A, right join B. What's going to happen is we're going to return all the records from B and the matched records from A. And the result is null from A if there's no match. So it's exactly the opposite, but we still talk about A being first. Okay, so we have the same setup, A, right join B. And now we're going to get a copy of B. So we have the rows 1, 2, 4, 6. And everywhere there's a row that matches an A, we fill in the field 1 information. And where there isn't, we fill in a null. So in the A, there's no 6. And 3, we never used it, right? Because B didn't have a 3, so we just ignored it. And when we got to ID 6 in B there was nothing in A, so we end up with a null in the output. Okay, now an inner join is where you're just focused on the intersection, where both data sets have a row that matches. Okay, so in an inner join, we'll return only records from the left A that match records from B. And if there is no match between A and B, the record is just ignored. Okay, so if we take the same setup again, we have A, we do an inner join B, we're only going to get rows where they both have the same IDs. All right, so we only end up with 1, 2, and 4. And this is because A doesn't have a 3 and a 5, doesn't have a 6, and B doesn't have a 3 and a 5. So we only end up 1, 2, and 4. So the inner join is you could think of it as the same as the joins we did before, where instead of inserting a null, we just ignore that row. We said, well, I don't want any null values in the output, so I'm only going to keep rows where everything joins nicely. Okay, and a full outer join is the opposite. It's sort of the optimistic join. I want to keep everything. So we're going to turn all the records from the left A and all the records from B. And if there's no match in either A or B, then we're going to put a null in for that field. So the same setup, we take A, full join B, and now we get everything. Okay, so all the IDs, we have 1, 2, 3, 4, 5, and 6. So we get in the output all 6 IDs. And you can see wherever there's a match, we get 2 values, and wherever there isn't, we just end up with some nulls. So in the B column, we have no 3 or 5. And so in the output in field 2, for 3 and 5, we get nulls. And in field 1, we get a null and 6 because the A table has no ID 6. So this is sort of the more optimistic join, if you will. Join everything and put in nulls where you need to. So let's go ahead and perform this same join on our data set. So I'm going to come back to the tree times extended, which if you recall is the one that we took our original data set and we extended it with the feature key. And now I'm going to do a join data set. And we're going to do a left join. This is where you could select the right join, full join, or an inner join. And now I need to tell it what data set to join. And so in this case, I want the tree times that we aggregated. So as we can see right here, tree times 1 aggregated. This is the one we want. And now we have to tell it what field from each data set to use to complete this join. In this case, in both, it's just going to be the feature key, but it doesn't have to be the same. You could be joining data sets where the field has a different name, and I see this a lot. I've seen this several times in normalization schema where you have the key in the tables is named an ID in one place, but it's just named a field in the other. And so it's possible that you could have something like, customer here, and over here it would actually be customer ID, even though it's the same value. I don't recommend doing that. I always find that terribly confusing myself. But if you run into it, you can still handle it here in the interface by specifying the name of each of the keys. So in this case, it is feature key in both, so that's very easy. We could actually add an additional join if we wanted to, but we don't need to. We just have this one table join to perform. And we can choose the fields that we want in the selected output, so we could list them all here, or we can just leave this button selected, which will join them all. All right, this button right there. So we'll go ahead and let the join run. Excellent. All right, and now we have all of the original fields. Plus, so here's the original status elapsed. Plus, from each table, we actually end up with the feature key. And now we have the aggregated value, the average status elapsed. And actually, while we're here, we don't need all these anymore. We don't need the original status elapsed anymore. That can go away. We don't need the feature keys anymore. We just created them to do the aggregating and the joining. So we can get rid of those too. So let's go ahead and go back to the dataset menu for a moment here. And we'll do a filter. And we will just create a new dataset where we remove those. So I'll just uncheck them. Goodbye, features. And now we have the dataset we were aiming for. The features for each tree that was built and the average time where trees with the same features have been collapsed into an average elapsed time. Problem number 3, though. The left join keeps all the records from the left data set. So remember in our original training set, we had this issue with the rows that were the same. Well, they're still the same rows in the output. They're just now, instead of having different values for the time in milliseconds, they have the same value for the average millisecond. So we have all the same original duplicated fields that we started with, but we've replaced different values with the average value. All right, this is still an issue for us. And so we can do this with a function called remove duplicates is how we can fix this. So we'll take this data set, which has, you'll notice, 8,189 instances, and we can go ahead and remove the duplicates from it, which is an option right here. And we'll go ahead and let that run. Excellent. And now you can see that it has removed 4,805, so slightly more than half of those records were duplicates. And so now we've achieved what we set out to do. We have a nice clean data set with no duplicate rows, where each one of these trees is a tree that has different and unique set of features, okay, that describe how the tree was built or the data set that was used to build it. And for every tree that was actually the same input, we have the average time that it takes to build that kind of tree with those kinds of parameters. Everything that I've just showed you, we can do through the API. So BigML is an API first company. Every time we bring one of these features, we always do it to the API first, and then our UI team is busily making the UI to make things easier to use, right? But if you have a programmatic mindset, or if you're building a real application where automation is going to be key, then we can use the API to do all these things as well. Moreover, the API has a much bigger set of functionality. So currently the UI has a limited set of data transformations. So in the aggregation, I showed you the options are available there, the joins and the removing duplicates. Now more functions are going to be added. Actually, concatenating is there. So between the time I made this slide and did this demo, I forgot to remove that. There's also going to be an option to do reordering, which is actually going to be a super cool function for what are called conditional windows in Flatline, where you can create a window that changes, that creates a feature based on a unknown number of fields, but you have to be able to sort them. So that's something you can do there. And we can also do multiple group bys in the UI. I forgot to show you, but instead of just grouping by one feature, you could actually do 2 or 3. You can do that as well. Now the API supports a nearly full SQL syntax for transforming data sets. Now I say nearly because nested queries are not supported, and when I say they're not supported yet, we're bringing that as well. So what is a nested query? So you might imagine a subselect. So if you're an SQL expert, I'm sure you've written a subselect at some time in your life. You can't do those through our API yet, but you will be able to soon. So now with this in mind, there is a better way to perform this entire workflow that I just showed you. So we ended up at one point doing this aggregation where we selected that column and the average of the status elapsed, and we did it from this data set. We grouped by the column that we're selecting, right, which was the feature key. But we could actually just do this in one SQL command. We could do the whole thing. We don't need to create the feature key. We don't need to do the joins. We don't need to do the remove duplicates. We could actually do this all in one aggregation, as long as we are allowed to group every feature that we put into the feature key. Now that would be very difficult to do in the UI because we have 13 or 11 features or something, so it would take a while to sit there in the UI and try to add them all. And I think the UI may only limit you to 5 or so anyways. So we'll do this in the API. Let me show you an example of that. To do that, I need the canonical identifier of our original data set. So here's our original tree times data set that we started with, right straight from the source, with all 8,189 and no feature key and no aggregations performed yet. All right, I'm just going to go up to the URL bar here, and I'm going to grab that canonical identifier. And I'll show you what this script looks like. I'll do a view. All right, so we start off by just establishing a connection to our API. Okay, my credentials are in my environment. There's a little bit of setup to make sure that you've specified the data set correct. But the crux of this is right here. I'm basically just doing a count from 1 to 16, because I know how many features there are in this data set, and building up a big list of column names by the hex values. And then we build up an SQL query where we just select all of those columns and the average of the elapsed time. And we say this from DS, and this is something we define internally. I'll show you in a moment. And then we just group by the same columns that we're selecting. So we just do a big giant group by. We group by every feature in the input. Okay, we'll see what that SQL query looks like when we run it. And then all we have to do is call the API create dataset function. We tell it what dataset to start from. All right, that's the dataset that I'm going to pass to this script. We can define this DS. This is where DS is defined. So the dataset that we're passing it is defined as DS for the for the SQL query. And then we just pass it the SQL query, and this will run in the API. So let's go ahead and do that. So there's the big select that it runs. So it selects all the columns and computes the aggregation, and then also does the group by with all of the columns as well. And so now if we switch back over to the UI, we'll be able to see that data set we just created, because our UI, as I mentioned, sits on top of our API. So that resource I just created is fully accessible in the UI as well. So here I can see the tree times 1. And actually, if we look at the one that we've deduplicated, so this is the one that was the output from the workflow I did in the UI, we can see it has 3,384 instances and 17 fields. And this one is exactly the same, 3384, 17 fields. And we can see this has the exact same output with the average status elapsed and all the original fields. So we can actually do that all in one big SQL statement. And if you click on this button right here, it'll actually show you what that SQL query looks like. So that SQL query is embedded in this object now as well, which is very relevant for what we're going to discuss next, which is how do we add new data and retrain. So tomorrow, our users on our software as a service site are going to build a whole bunch of new trees, and I want to build a new model so that I have better predictions for how long it takes to build these trees, for example. Or I could do this similar workflow for deep nets and everything else too as well, of course. But how are we going to do that? So when we add a new batch of data, we want to avoid re-uploading by using a merge. So I don't want to re-upload the tree times 1 file. It's already in the platform. I've already done all this merging and everything. I don't want to do it again. And so what I'm going to do is upload my new data and use a merge. So I'm going to repeat the entire workflow on the merge data set using Scriptify, and then I'm going to merge those two output data sets together. So I'm going to take this data set and the new data set, and I'm just going to glue them together in rows. So because this SQL statement is embedded in this data set, I can actually turn this data set transformation into a script. So I come up here and I can say scriptify this data set. And this is going to generate a script in a language that we call WYSML. It's a domain-specific language for creating workflow automations. And that workflow in this case is going to exactly reproduce that data set transformation that we did to perform the aggregation. And so we can actually look at the source code and we can see, it should be in here. There's the exact same SQL query. It's now embedded in the script. I didn't have to write it again. We could do this from the UI resource as well. So I could just sit here doing transformations in the UI and then in the end scriptify it. And what we end up with is a script that we can now apply to a new source. So let's go ahead and do that. Let's bring our new data in. So I'll upload the tree times 2 sample here. So imagine this is our data that we've collected for tomorrow. So tomorrow I collect all the tree data again, and I upload it now as tree times 2. And I have this source, but now I want to do the exact same transformation. So I can switch over to our WYSML menu. I could actually take this script right here, and I could put it on. I could actually put it directly onto our sources. So by clicking there, that script will now show up. I could even make it a one-click action. So now when I go back to the dashboard, any source that I'm looking at, I'll be able to actually execute this steps for tree times 1 script. So now it's going to execute that script on the new tree times 2 source. So it's taking the new source I just uploaded and applying the exact same SQL transformation. And so we're going to be able to see in the resources, it's now creating a data set, and then it'll create the transformed data set, and there's the output. All right, so here's the output for tree times 2 with 3,669 rows, and now I want to glue them together, so I can do a merge, and I can just merge this into tree times 1. So now I'm taking tree times 1 and 2 and creating a new output data set that has the rows from both of them combined together. And so now you can imagine I could just every day upload a new source, run that WYSML script, and merge them together. And now I have a nice training set that compromises the processed rows from both uploaded files. Okay, so if you're looking for more information, we have the URL to the releases page there, which we'll go through, and you can see the series of blog posts that we've created, all of the documentation for the data transformations features that we've added, and the information is all there.